All right, guys, welcome back to week 2, and this is the main topic for this unit, at least for this year. It always is, but lots of times we spend a little bit more time on what we did last week. But this is what we're going to take a look at, something called electron configuration, and there's actually something called electron configuration here, but there's 4 kind of styles or 4 different types to do this. We're going to start with the most specific that gives us the most information, and we're going to break it down to the easiest one that gives us the least amount of information. But before we do that, we got to talk about the rules and stuff that we need for that. All right. So electron configuration, all right, is the arrangement of electrons in an atom, just like Bohr's model, right? The same idea, but we get away from the rings, right? We're going back and we're looking at Schrodinger's and his parts and pieces, his 4 numbers, but we're going to be a little bit less specific in exactly where those numbers are on the periodic table and just place them in order in a couple different ways so we know what atom we're looking at. Okay. And the key of all of this is, remember, atoms they need to be lazy. And again, another way of saying that, they need to be in their ground state, right? They need to build up. They need to have those electrons as close to the nucleus as possible, whether we're looking at Bohr's rings building out like that, or we look at something like this, where we start to see some of Schrodinger's numbers and levels, right? And orbitals, right? And then we're going to put our electrons where they need to go. And if they want to be lazy, that means we need the least amount of energy. Okay. And if you just look at this chart, you might be able to figure out how the heck we're going to build based off this. Okay. And so we have 3 rules that we need to take a look at. We're going to break each one down, and then we're going to apply them as we go through this. Okay. So the first rule is called the Offbow Rule. And I love saying that. I love saying Offbow. What it means is it goes directly back to Bohr, and it means electrons always occupy the lowest amount of energy first, right? They want to be lazy, so they're going to fill up the spot where it takes them the least amount of energy to do so. Okay, and so Offbow means building up. Okay, in order to occupy the lowest amount of energy, you have to build up. Meaning, if we go to and we think about building a house, you got to build the foundation, right? Then you build the walls, and then you build the roof, right? If you don't do it in that way, it is definitely going to take you more energy to try to make this roof hover and then try to build the walls under that and then somehow build or pour the concrete after that. That doesn't make any sense. And it doesn't make sense when we're building atoms either. All right. And so we have an order, and I'm going to give you the list, but it's not something we need to memorize. The periodic table is actually going to give us this, right? As long as we read the periodic table from top to bottom and left to right, just like we read a book, we'll be good to go. All the information's in there. There's some tips and tricks that we need to talk about, but this is what we were trying to start when we were taking a look at Schrodinger's model of the atom last week. So like I said, just like a book, here's the order. Get my face out of the way. So we have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. All right, you don't need to memorize that. As long as you can read as long as you can read left to right, top to bottom, you're good to go, right? The periodic table will show us this. And I have a couple other things I'm going to show you here in a little bit that'll kind of help us look at what this is. But basically what this order is, this has the lowest amount of energy. This would have the greatest amount of energy. Okay? And there's a pattern, there's a trend, and the periodic table is built off this pattern and trend. So what we're going to get to is something that looks like this. Now, we're not going to build this up and kind of make it 2-dimensional like this. We're just going to build long sequences of this. But all the parts and pieces that we need are here. And what I want you to realize is we're seeing the same things that Schrodinger gave us, right? So think about like the number 1 down here, right? The number 1, the number 2, the number 3, the number 4, the number 5, the number 6, the number 7. Where do we find those on the periodic table? Right? Another name for those numbers is the period numbers. Well, what Schrodinger called them is he called them his energy levels, right? Or those are the states, right? The bigger the number, the bigger the state, okay? Because we can have more stuff that fits in and around them. So we can see those up there, and we can see more of the numbers over here, right? And you don't see every number for every part and piece. And then here we have these sublevels, right? So you can see the S sublevel, in the P sublevel, in the D sublevel, in the F sublevel, right? And those were our cities. And the S's are the smallest city, right? P's medium, D's are bigger, F's are the biggest city. Okay, so we have our cities, and then we have our streets. So S's, they only have one street, right? They have one box in this case. And then P's, they have 3 boxes. D's, they have 5 boxes. F's have 7. Okay, and those boxes are the orbitals, right? These are orbitals. So we can see that we have the energy level, we have the sublevel, right, which helps us know where we are in the periodic table. You should be able to find your 3s on your periodic table, right? And then here we have the orbital. Now for S's, there's not much of an orbital difference. Here we have 3 orbitals. Now we call this the X, Y, and Z, or we numbered these -1, 0, +1. We're not going to worry about that anymore. If we had more time in the year, we would, but we're not going to worry about that anymore. We're just going to start to use these, and we're going to start to build these. And like I said, here's our foundation down here, and we're just going to build up as we go. And you can see there's some levels that are kind of in between, and this is why Bohr's models didn't work. We need this variation. We need these slight tweaks, these slight differences to make these work, right? But basically, the farther you are up here, the more energy you have. So you're not going to be all the way up here unless we're exciting you. If we're just building a normal atom, right, if we're at our ground state, we're going to be down here and we're going to build up. Okay, that's what Offbow says. Okay, here's another way to look at Offbow instead of memorizing it. If we just kind of put these in order like this, if you just follow this green-blue line, right, you go right in order. That's nice, and that is a different way to look at it. Some people like that. We start a hydrogen at the 1s, and then we go to the 2s, and then we go to the 2p and the 3s and the 3p and the 4s, right? And so you can kind of arrange these this way based on their energy levels, right? And then based on putting in their sublevels, right? And you just kind of order them up, and you can snake your way through it. Great, that's nice. But honestly, the easier way is just by knowing a few tips and tricks on the periodic table. I already had you do this, right? If we read left to right, top to bottom, we're good to go. So we go from element 1 to element 2 to element 3, element 4, element 5, element 6, right? And we just keep on snaking our way through. And the only couple hiccups are right here. Notice this. You go from a 4s to a 3d. This is why Bohr's model broke down, right? There is not as much energy with the D elements as there are with the S elements, right? That's why they're slightly underneath. So in order, because of their protons, they're here. But based on energy, they wouldn't be here. They would actually be shifted up. But because we build our periodic table and we build atoms based on protons and electrons, we have them there. So we go 4s, 3d, we come back to a 4p. So p's again at the top. P is greater than s, but it's also greater than that d, right? And then we snake back and we come back here, 5s, 4d, right? So we have one number less. And then we go back up to our energy level, right? We go to 6s, right? And this is where it gets really different. We go 6s, and then we'd actually jump down here to 4f, and we come back up to 5d and 6p. Because if we look at the alkali or the lanthanide and actinide groups, right, they come in right here. And we'll deal with that at the very end. I'll get specific. We're going to do the easy ones first. I'll leave the hard ones for the very end once you've had some time to kind of figure this stuff out. So just realize we're going to have to deal with this F block, D block transition. It's a little bit more difficult than just right up here, but we'll be able to do it. Okay. So the second rule, so we had Offbow's rule, build up. Hunds Rule, right? Hunds Rule says orbitals of equal energy are each occupied by one electron before any one orbital is occupied by another, right? So once we know our energy level, once we know our sublevel, then we need to look at our orbitals, right? Our orbitals were the third number that Schrodinger gave us. So S's have 1, D's have 3, or P's have 3, sorry. D's have 5, and F's have 7. Oops, which way is the camera? Good, right? So what we need to do is we need to apply this rule when we see orbitals. You got to put one electron in before you can occupy any other one. Okay, now that doesn't make a lot of sense right now because we hadn't had to do that yet, but it's going to once we start building them. All right, and the reason for this is because of energy, right? The reason why we have this rule is we're trying to decrease the amount of energy as much as possible. Even though we're adding more electrons, and adding more electrons means more energy, we are trying to decrease it as much, okay? Because atoms want to be lazy. We know that. We're trying to decrease the energy because atoms want to be lazy. And the real reason we need to separate them is because of this. Electrons are both negative. And so when we bring two negatives together, they like to repel. And so the repelling means that we have more energy to keep them together, right? It takes more energy for us to keep them together. So if we can separate them first and then only put them together when we have to, that is what keeps energy low. That is what keeps the atoms as lazy as possible, right? And so I'm going to show you this. Okay, so right here for Hunds rule, basically S's, right? They have a single orbital. It doesn't make a difference. Okay, so to go from an S, you only have one orbital, so you only have two electrons to place in here, and they both go in. One would be going up, and one would be going down. This is where the spin comes in. You can have one positive, one negative, one up, one down, one left, one right. However we want to think about it, they're there. Where it changes is when we get to a p sublevel and we look at the three orbitals, right? If we're going to place two electrons in here, right? Remember, these are the streets. I don't know about you, but I don't want to have a neighbor right on top of me. So if I'm going to build my house on a street, right? If I have a neighbor right here, I'm not going to build right next to him. I'm going to go over to the next street and I'm going to have my own property and I'm not going to worry about it. And again, if we got in another guy and we have our third street in our city, they're going to build over here. Not until we have one electron in each one of these orbitals are we going to start adding a next one, right? So once we have one house on each one of these streets, then we'll come back and we'll add in another house on the opposite side of the street. Or in this case, we'll add in another electron, right, within these orbitals. And same thing with the Ds. So Ds down here, we're going to add one electron into each one of these orbitals before we ever come back and we add in the next one. Okay, and again, I know this is still ambiguous and up in the air a little bit, but when we start actually building these, you'll see where these all hit. Okay, last rule before we try to build our first and most specific type of these. It's the Pauli exclusion principle. Okay, this says that the electrons can't have the same set of four quantum numbers. It means their N, L, and M and S all have to be different. Okay, three of the four can be the same, but one has to be different, and it's usually that S. So what it's saying is the spins, right? If you're N, L, and M, if you are in the same state, in the same city, on the same road, you have to live on opposite sides of the street, right? That's what happens. The spin has to be different. This is where a positive and negative come in. We're actually just going to draw that out, right? They got to be opposite. Now, one of the keys is when we're drawing these, you have to have a positive spin first. It's got to be an up arrow. And I'll show you what that means. All right, so you have to do in your up arrows. And if you actually go back and you look, that's how the periodic table is built. That's where we're not being as specific this year. We just want to remember this, not actually where the positives and negatives are on there. So again, if we were to do this, and I wish I could draw on this, but really what we'd have is I'd put in an up arrow and then a down arrow, right? I'd put in an up arrow, an up arrow, an up arrow representing electrons, and I'd come back and I put in a down arrow, a down arrow, a down arrow representing electrons. Okay, and when I draw these out, that'll be more obvious. Okay, so let's work with our first one, and then we'll call her a day. All right, so the first type of electron configuration, the most specific one is called orbital notation. This is where we're going to draw everything we just talked about, right? And then we're going to simplify it. The problem with simplifying is we got to understand what we're doing because we take in assumptions, but we're going to simplify them as we go. All right, so the steps to this, the first one is we need to know how many electrons we're going to build, right? And we need to understand the pattern of where they're going to go. And then we're going to give the N and L and build up to that element. Okay, so we're going to get that build up in there, giving the state in the city, or we give the energy level and the sublevel, right? And then we're going to represent lines as orbitals. So these are going to be horizontal lines, or like we saw earlier, boxes. And then arrows are going to represent the spin. So that's why you saw me, or you heard me say earlier, an up spin or a down spin, a positive spin or a negative spin. We're going to represent that with arrows. Okay. And so in this case, we're able to show all three rules. That's why this is the most specific. It's the most time consuming, but it's the most specific. And so we're going to try a few of these. So I'm just going to give you one right now, and then we're going to do three together. So you're just going to be able to see the answers right now of what a sodium would look like. Okay. And so this is what sodium, we have sodium, and we can see down here, all right, we have, oh man, this is in the way. Can I get rid of that thing? I'll try to do it without my cursor. All right, so you can see on the bottom, we have 1s in yellow down there and 2 arrows. And then we have 2s with 2 arrows. And then we have 2p. And the reason that 2p is right there is there are 3 orbitals, which we see, and there are 6 arrows in there. And then we get back to our 3s over here with only 1 arrow. And again, that might not make any sense to you yet, but we're going to build them from scratch, so this makes more sense. Another way we can look at this is kind of what we were looking at before. Same thing. We're not going to build them this way and worry about the verticalness of it, but this also shows the energy. This is based on energy increasing this way. This is just based on a vertical, and it just gives you a little split of it, but you can see the same thing. There's 2 in the S1, 2 in the S2, 6 in the SP, and 3 in the S1. If you add all these up, they equal 11. Why should they equal 11? Because sodium has 11 electrons, right? So if we know that, the number of electrons, and we know the basic sequence, or we're able to look at the periodic table, these aren't that bad. It's just knowing when it's right and when it's wrong. And so we'll take a look at that. All right, so what we're going to do is we're going to build these up, and I'm going to do it on paper. And we'll kind of look at them together. And we're going to build these same 5 with the different types that we're going to take a look at this week. And so you can kind of compare and contrast and see the difference. So I'm going to write them down on my piece of paper, and then I'll transfer over to my calculator, or my camera, and then we'll take a look at this. And then bromine. Okay, so I am going to turn this on, maybe. Come on, baby. So not let me do it because I'm in there. There we go. Do this. Okay. So again, these are just examples. Write them down. Try to think as I'm thinking, and then we'll have time in the coming days for you to practice what I'm showing you right now. And so if I have carbon, the one thing I want to know is how many electrons carbon has. So if I come back here, right, and I'm looking at my periodic table, what I know is, all right, carbon right there, it has 6 electrons, right? We've done carbon quite a few times. And so if I know that, that's great. That's my check, right? And so I'm going to start with what I know. And what I know right now is I have the first energy level, right? And the first energy level runs into my S sublevel. All right. Basically, I'm telling you, hey, I'm right here, right? This is 1s right there. Now, with these guys, this is why I'm talking your orbitals is a horizontal line, okay, which S's only have 1 orbital that we learned from Schrodinger. And so I'm done right there. And so with Offbow, I build up by putting in 1 electron. Okay, there's my arrow. Yes, it only has 1 head because it's easier. If you want to write 2 heads, that's fine. It just takes a little while longer. And then Offbow says to build up. Well, I have my energy level, I have my sublevel, I have my orbital. Orbitals can each hold 2 electrons. So I'm going to put in my opposite arrow, which is the combination in this one of the Pauli exclusion principle and Hunds rule. And there we go. We have 2 electrons built. Then I'm going to go to my 2s. So right now, what I just did, my 2 electrons, if I stopped right there, I'd be at helium, right? 1 up, 1 down. All right, now I'm jumping over to my 2s. So my 2s is right here. Okay, again, s's have 1 orbital. And so I'm going to put in my up arrow, and then I'm going to put in my down arrow. And right now, I'd be at beryllium. Okay, so far, pretty good. So I'm going to jump all the way over here to boron. Okay, and I'm going to start putting in my my elements. So I'm still at energy level 2, right? I'm still at energy level 2, but now I've reached my P's. Okay, and what we want to remember is there's 6 elements as we go across here. In every orbital, every street can only hold 2 houses or hold 2 electrons, right? And so we need 3 orbitals in order to hold all of these guys before we get down over here. And so that's what I'm going to do. I'm going to put in my 3 orbitals. Okay, now according to Hunds Rule, it says in order to fill this up, I need to put in electrons in opposite or in different locations. In Pauli exclusion principle, it says I need up arrows first. So I need 2 more electrons, right? I'm trying to get to 6. And so in order to do this, either I'm going to put an up arrow and a down arrow there, or I'm going to put 2 up arrows. Which do you think I'm going to do? Right? The correct answer is I'm going to do an up arrow and an up arrow. And the reason I do that is less energy. Those are both negatively charged electrons. I'm going to put them on opposite streets. I'm not going to build my house right next to somebody unless I absolutely have to. And carbon's done. And we know that because we have 6 electrons. And according to our rules, we've supported each one of the rules. All right. So let's take a look at fluorine. Fluorine now is over here. Right. So fluorine, we have 9 electrons. So same thing. And this is where this gets a little repetitive. I've already built carbon, so I'm going to build up to fluorine. So I'm just going to do that part fast. I'm going to start up here. Here's my 1s, and then I'm going to go to 2s, and then I'm going to come back at 2p. All right? So I have 1s. Good. I'm helium right now. And then I'm going to go 2s. 1 orbital, 2 electrons because I'm building up. And then I'm going to go to 2p, 3 orbitals, right? And in this case, because I am the 1, 2, 3, 4, 5th element over, I know I need 5 more electrons, right? And I know that because I've already drawn 4, and I need up to a total of 9. So I need 5 more. And so what is that going to look like? This isn't that hard, but I would still probably try to do it this way, is put in your 3 up arrows, just like Hunds Rule says, and then come back with the Pauli exclusion principle, which says, all right, I'm going to start doubling them up now because Hunds Rule says I can, but now I need an opposite arrow. I need to be on the opposite side of the street. And there we go. Right? That's that guy. Oh, no, sorry. Oh, gosh. I was getting too far ahead of myself. Beep. There we go. That's it. That should only have 5. If I did that, I would have been neon, and I don't want to be neon yet. All right, so now we are going to go all the way over here to phosphorus 15, right? So these start to get pretty big, which is why we do these at the beginning, and then hopefully we don't have to do them too much more at the end. So again, I'm going to build up 1s, 2 electrons, 2s, 2 electrons, 2p, 3 orbitals, 6 electrons. So right now, again, if I ended, I'd be right here at neon. Okay, so I'm coming back down here. So down here is my 3s, right? And we know s's have how many orbitals? They have 1, right? And I'm going to put 2 electrons in there because that's all I can do. So I'm at magnesium right now, and now I'm going to come over to phosphorus, right? And so that means I'm going to come to my 3p. How many orbitals are in a p? You need to write them all, even if you don't use them all. Okay. And in this case, there's multiple different answers, and this is where you need to understand the rules. If you only draw in 3 electrons, if you draw in 3 arrows in just random spots, it won't necessarily be right. Right? You'll be close, but not good enough. So I need to draw in up arrows first. 1, 2, 3. And that is what I needed. And I'm done right there. All right. 2 more. Okay, just to give you some guided practice, right? Magnesium. So magnesium is back at number 12. Okay, so if I'm going to do magnesium, I need to come into, actually, I'm going to change that to manganese. Let's do one of these guys. That's probably what I wanted at the beginning. So manganese is right here, right? We have our first D block element. First D block, 25. All right, so I'm going to go back to, and start at the beginning. So I'm going to go quick, 1s. All right, 2s, 2p, 3s, 3p, and then I'm coming back down here to my 4s. Right, and now I have my D's. The first time we run into a D, and what is a D? A D is 5 orbitals, but remember, they are one number less than the S that's in front of them. They don't have as much energy, right? We have them after them because that's how the protons work out, but not how the energy works out. So I'm going to come down here just to save us some time, and I'm going to put my 3D right here. Now, D's have 5 orbitals. Right? 5 orbitals. And for manganese, I am 1, 2, 3, 4, 5 more than I need. So guess what's going to happen? I'm going to come back here. And I am going to put in my 5 electrons. And I end up with manganese. Right? A really nice look. Last one. We're going to come all the way over here to bromine. Right? You can't see it. We're going to come all the way over here to bromine. All right, so for bromine, again, starting in the beginning, 1s, 2 arrows, 2s, 2 arrows, 2p, 3 orbitals, 6 arrows, 3s, 2 arrows, 3p, 6 arrows. All right, I'm going to put my 4s right here, 2 arrows. I'm going to put my 3d, 5 orbitals. We're going to go all the way through it. So I'm going to do my 10 arrows. All right, and then I'm going to end back with my 4p. How many arrows or how many orbitals does it have? P's always have 3, right? How many do we need to place in there? Well, we're up to 30, and phosphorus or bromine has 35, so we need 5 more arrows. So again, 1, 2, 3, 4, 5, and I have my bromine. All right, next time we are going to look at a faster, easier way to do this, but a way that also doesn't support all of our rules, so they're also sometimes easier to screw up or to look at them and think they're right, but they're really not. All right, have fun.